Way better.
Okay, we're recording.
I don't know what we're doing. How can I help? What questions? All right, we're ready.
Joey, right here.
Go. Yes.
Maybe just confirm if something's moving closer to you, but it's slowing down, then the frequency is not going up,
Really good.
right?
The question is about Doppler shift, and I think I can simplify. So the things you need to know about the Doppler shift. First is the relative motion is towards the source, or the source moving towards you. The shift is to a higher frequency. Second thing, if you're moving away, source is moving away from you, or you're moving away from the source, the shift is to a lower frequency. And the last thing is that how big the shift is depends on the relative speed. So if I can just draw a graph here. As a function of time, if we plot the frequency that you hear, and let's say that there's a police car with a siren playing at 400 hertz. If that police car is coming toward you, you're going to hear something higher than 400, like 410. And if that police car is coming toward you at constant speed, they're going to always hear 410. Now, this difference between what you hear, the police car is creating for sound, is called the shift, the Doppler shift. And if it were coming faster, that shift would be bigger. So if we take, this is the car, remember, that's coming towards you. If that car is speeding up as it comes towards you, the shift is going to get bigger, and what you hear is going to do that. So that's speeding up. If that car coming towards you is slowing down to a stop, the shift is going to get smaller. And when it stops, you're same frequency that the car siren is making. Now, on the other hand, if that police car is driving away from you, you're going to hear it shift down, say like 190 hertz. And if that speed of the police car is constant, that shift will be constant. Now, again, the size of the shift depends on the speed. So if that police car moving away from you speeds up, the shift away from 400 is going to get bigger, and the frequency that you hear is going to go like that. On the other hand, if that car going away from you is slowing down, the shift is gonna get small. And eventually, there will be no shift. When it stops, you'll hear the 400 hertz. So this would be slowing. This would be slowing. This would be speeding up. And this would be away. So. Yes.
Is the line straight like that because it's constantly going away from you and constantly coming towards you? Does that make sense?
This one here? Yes, that's got cruise control on, say 60 miles an hour.
If the frequency wouldn't change as it's coming towards me at a constant rate.
If it's coming, if the siren's coming towards you at a constant rate, you're gonna hear something higher than what it's making. But that higher note is not gonna change. So it might be making a middle C, you're hearing D. But you're hearing D, 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 D.
It wouldn't change as it got closer. That's not
No.
what matters.
It would get louder, but louder is really easy. It's the softer it is, the louder it is, the further away, the quieter it is. Experience in life teaches you that. Samuel?
So it's like a good, so I guess like as a good example, so if let's just say a police car is going towards you and it's always at a constant speed. Because it'll be towards you at a constant speed, it's going to stay at a constant high frequency.
Yes.
And then once it passes you and it's still that constant speed, it will always go constantly at a lower frequency.
Right, and as it passes you, you hear what we heard at the racetrack. Cause it was shifted up 10 hertz. As it's going away from you, it shifted down 10 hertz. It just changed by 20 hertz as it went past you. Yes, sir.
So would you say that at that moment it's going by you at 400 hertz or would or is it like instantaneous or just goes from?
Yeah, let's not worry about whether that takes a tenth of a second or a hundredth of a second. That's not gonna be on the exam. Yeah, yes.
So then as the shift increases, is it speeding up? For example, if it's speeding up while it's coming towards you, the increased shift, does that mean that we're hearing a higher?
It means the difference between the 400 hertz and what you're hearing is getting bigger. The spread is getting bigger.
So as that spread is getting bigger, does the note we hear change?
Yes, oh yeah,
So it's gonna be getting,
yeah, so if we take this case here. If it's making, if the siren's making a middle C, then you're gonna hear a D as long as it's going constant. And then you're gonna hear E, F, whatever comes after F.
okay,
Again, I don't know music.
perfect, thanks.
Yeah. The frequency is the pitch. How far to the right on the piano you are. Okay. You're on Doppler shift. Good. Definitely a question on Doppler. Yes.
So is this exactly the same if you're going towards the sound source?
Oh, I can't hear that. I'm sorry. Let me come back. What was that?
If you're going towards the sound source, like if the source is stationary and we're coming towards it, is it the exact same?
Exactly the same. It doesn't matter whether you're going towards the source or the source is coming towards you. It's exactly the same. Okay. Other questions? Yes, sir.
Go over displacement, size, and direction of points on a standing wave. The displacement, size, and the direction of points like on a. standing wave.
Oh, yeah. So when we have an organ pipe, Well, first of all, let's deal with the easy case of a guitar string, okay? If I have, say, the third harmonic, what that's gonna look like is three footballs. It would look like that one instant, and then a half a period later would look like this. And the individual parts of the string, these guys would be displaced from equilibrium this way, and these guys would be displaced this way, and these guys would be displaced this way, and then 1/2 period later, then reverse. And where I have a node, there's no movement. And where I have an antinode, that's the fattest part of the football, I have the most movement away from equilibrium. So now, if we look at an organ pipe, and why not? Let's look at the third harmonic again. Okay. The football representation really doesn't do the thing justice. It just tells us where the nodes are and where the antinodes are. Now, whereas in a string, the node is just a single point. It doesn't move. But in an organ pipe, the location of the node represents a whole layer of air molecules, okay? And all of these points are at a node. None of them are moving during the whole process. Likewise, I have a node here, and none of these are moving. And likewise here, none of these are moving. Now, if I'm told that a particle here is moving this way, that tells me that this node right here is being deserted. And that means that the neighboring node is being crunched and its neighbor is being deserted. Remember, the whole standing wave longitudinally is just sloshing, like if you're in the bathtub scooching your bum, okay? And you get these nodes that are crunched and then deserted and then crunched and then deserted. Yes.
Is the node in the or
I'm sorry.
is the node in the center? Like, how do you know which one is crunched and which one is deserted?
Oh, well, they all take their turn between being crunched and being deserted. If you were told in the homework that this particle was moving to the right, and all the particles in a single football move the same way. So all the particles in this football are racing this way, and the fatter the football, the bigger the displacement. Over here, they're just moving a little bit. If this node is being deserted, it's being deserted from both sides. And where the football is fattest, they're moving the furthest. And if this one's being crunched, it's being crunched from both sides.
Where it's fattest, they're moving the most. And this one's being deserted from both sides. And where it's fattest, it's moving the most. Now, if the period of this oscillation is 3 seconds, in exactly 1.5 seconds, all of these arrows are going to be reversed. That's what the sloshing is. And so this node here was being deserted when we took the picture. If we took the picture half a period later, it would be crunched and the neighbor would be deserted. Stephen?
So in order to know which is crunched or deserted, we need to be given at least 1 point.
Yes, you have to know at least 1 point to know which one's being crunched and which being deserted when you took the picture. Yeah. Yes.
So in one of the practice exams, it just gave us like one end of the degree was closed. So how do we know, but it was, how do we know like how to sketch it out? You know what I mean?
Sorry,
One of the practice exams, it didn't give us like a point, it just gave us this. So how do you know?
Right, but they didn't ask you which way they were going. They just asked where they were moving, where they weren't moving. And at the antinodes are moving the most. Nodes, not at all.
Yes.
May we go over reflection and transmission of the big waves?
The what?
The reflection and transmission in waves. May we go over that?
Oh, sure.
Thank you.
The key is that we have a boundary between a fast wave, fast spring rather.
Dr. Francis, we can't see that.
Thank you. We have a boundary between a fast spring and a slow spring. And if, let's say this one over here is the fast spring, and this is the slow spring. Okay, just for concreteness. If a pulse comes in, we call it the incident pulse. Or I call it the mother pulse. Okay. When it hits that boundary, it splits in two. Okay. And I call those the twins. And one of those twins is the reflected pulse. Reflected just means bounce back into the original spring. And the other is the transmitted pulse. Transmitted means goes on into the other spring. Okay. Now, if I'm going from fast to slow, what that really means is I'm going from light to heavy. And I know that because the speed depends on the tension divided by the mass density. Well, they have to have the same tension because they're pulling on each other. By Newton's third law, which remember we learned, they have to have the same tension. So this is going to be the same. And so that means whichever one is heavier is going to have the smaller speed because the mass is in the basement. The bigger number in the basement, the smaller thing I get. Okay. Now, if I think of the light one as a fishing line and the heavy one as a chain, if I'm going from light to heavy, this boundary is going to act like a fixed end. Now I know from that next to the last tutorial that when I hit a fixed end, the reflected pulse inverts. If it was on top, it comes back on bottom. If it came in on bottom, it goes off on top. It inverts. And so that means that when these guys, when they split, the the reflected one is going to be inverted. It's going this way. And you'll notice that the leading edge, the edge that's leading the charge, is still the leading edge. The other thing you'll notice is that the width of this pulse, the mother pulse, is the same as the width of the reflected pulse. Okay. Now let's talk about the transmitted pulse. The transmitted pulse, yes.
How is the amplitude change? Or
The amplitude is just complicated, messy. What I can say is because some of the original energy in the mother pulse had to go into the transmitted pulse, the amplitude of the reflected pulse will always be smaller. But the transmitted pulse can sometimes be bigger, sometimes be smaller, sometimes the same. It's very messy, and I would never ask that on an exam.
Okay.
Just the width, just the width. Okay, now, what do we say about this transmitted pulse? Where should I draw it relative to the boundary? And how wide should it be? Yes, sir.
It should be on the same side as the incident pole.
Okay,
It should be smaller because the figure's been
right, and how close to the boundary?
closer.
Closer, yes, because they were both born midnight at this hospital right here. And the transmitted one didn't have, it was going slow, so it didn't get very far away by the time I took this picture. Okay, but it will always be on the same side as the mother pulse. This is the transmitted. Now, what if I come in? What if I come in on the other side? And just for fun, I'm gonna come in. Let's say this is the, still the slow and the fast. I'm gonna come in with a pulse like that on the bottom. Well, when it hits the boundary, now I'm going from heavy to light. And so this boundary going the other way is going to act like a free end. And that means the reflected pulse is not going to invert. It's going to stay on the same side. And so when I draw the twins, well, the reflected is going to be on the same side as the mother pulse. In this case, it was on the bottom. And the transmitted is always on the same side as the mother. And you see that the steep side of this pulse was the leading edge that was leading the charge. And it's also the leading the charge for the reflected. And it's leading the charge for the transmitted. Okay. Now, the type of question that you are likely to be asked on the exam is going to be showing the twins, saying these are what the twins look like 5 seconds after midnight. The mother pulse is already split in two. Which side did the mother pulse come in on? And what did she look like? What was the shape? Was she on top of the spring, on bottom of the spring? And you know that the thing that you want to look for first, are the twins on the same side or opposite side. If one's on top and one's on the bottom, you know the reflected pulse had to have inverted. Because the transmitted never does. Okay, the only way they can be on opposite sides is if it was like hitting a fixed end. And that tells you right away that it had to come in, the original pulse had to come in on the fast side, the light side, and hit the heavy side. So then you look at the twins to see which side is fast and which one is slow. By looking about how far they are away from the boundary when we took the picture and how wide they are. It's gonna be wider for the fast wave, narrower for the slow wave. Yes, sir.
Will it always say which one's the leading edge on which side?
Sorry, I'm so deaf tonight.
Will it always say which side's the leading edge? Like,
Do you need to say, or?
which is the leading edge?
Oh, no, the leading edge, when you're looking at the twins, they're racing apart from each other. And so you immediately know which is the leading edge, because it's the part of the pulse that's leading the charge away.
Right.
Okay. Now, if I were to give you, say, these twins and ask you, well, two questions. Which side did the mother pulse come in on? It's multiple choice question. What you would say is, well, it had to be coming in on the fast side because it hit a fixed end. And then if I asked you, well, what was the shape of that mother pulse, and gave you a whole bunch of different shapes, some upside down, some right side up, some with the leading edge over here, you would have to pick that one out of a lineup, just like going down to the police station and finding your mugger. So you think you could do that? Good. Yes.
So a good rule that I kind of use when doing the tutorial was that if the pulse, like the pulse with the greater width or the greater length per se, is the one on the spring that's faster.
Yes.
Or the one that's lighter, technically.
Yes.
So is that like a good rule of thumb to have for this?
Yes. It is an excellent rule of thumb. It'll be wider and it'll be further away from the boundary.
Okay, will the problem always say which spring is lighter or heavier, or are those
No.
sometimes we have to figure
No.
it out?
And I feel guilty admitting this. But I have in the past, I'm not proud of it, but I have drawn the twins with the two springs. And the spring on one side was in dark black. And the spring on the other side was light gray. And people just jump, oh, that's a light one and that's the heavy one. Because light is light and heavy is dark. And it worked. And of course, I did it just the opposite, just to be mean. Well, let's call it what it is, evil. So don't look at the color of the spring to give you any information. Look at where the twins are relative to the boundary.
Should we worry about frequencies through water?
Worry about,
The frequencies through water like we did that one day or not?
oh, she's asking what's on the exam. Yes.
Awesome.
What we know is that the frequency of a wave is always, always, always equal to the frequency of the disturbance that causes it. And so when we had that sound wave going from air to water, it was the sound wave hitting the water. If it's hitting the water 10 times a second, it's sending pulses through the water 10 times a second. And what we found in that last tutorial was that whatever frequency I had in the slow medium, I had to have the same frequency in the fast medium and vice versa. What changes is the wavelength. The faster speed is gonna have the bigger wavelength. Because speed is just wavelength times frequency. The frequency doesn't change. Wavelength's gotta control it. Okay. But now that I think about it, no, there aren't any questions about that on the exam. Josh.
So you know on like the equations for simple harmonic motion, like the t equals 2 pi square root of like a. There's two other equations. Do we ever need to know like use the r over g 1 over q for anything at all?
No, we decided, and by we, I mean royal we, decided not to go there. That the mass up and down on a spring was enough. However, you're going to be parents someday. And I just want you to know that the most terrifying words that a parent can hear are, I have a science fair project due tomorrow. Okay? And if that ever comes out of your child's mouth, do the pendulum. There's just so many ways you can make that the winner. You change the length of the pendulum, you change the mass on the bottom of the pendulum, and pretty soon you get that formula that we decided not to use. My son did that to me, and we did the experiment late at night. He turned it in, and his teacher accused him of using his father. But he did it himself. He's just a type A individual. Yes.
Okay, I was wondering, I don't know if we need to know this for the test, but I remember one of our homework questions talked about how pulses change, like when you're on the moon with open gravity. How would it change exactly?
Well, what you know is that the tension in the wire changes in that homework problem. So that means the speed of the pulses changes. But the mass density, you remember mass, we learned doesn't change when you go to the moon or anywhere else. Mass is something that is universal everywhere. So the mu in that formula doesn't change. But because the tension does, the pulses slow down. Yes.
So how do we know, like, if we had to find K, the spring constant, how do we know if we use Hooke's law or the equation for tension?
Yes, very good question. The key to knowing whether you, the static approach with Hooke's law or the dynamic approach with that formula for period is exactly in the name, static versus dynamic. If something's moving, bouncing in the problem, you're going to want to use the dynamic method, which is that. Okay, you figure out what the period is in seconds, and then you can find K. Now, I hope that you've all practiced this math. It's not hard. If I square both sides, I get t squared. 2 squared is 4, pi squared is pi squared. The square of this gets rid of the square root sign. And now I can cross multiply and get. Yes. Now, if on the other hand, nothing's moving, you had a spring or a bungee cord and you pulled on it either by pulling with your hand or by hanging a mass on it, then you would find it with Hooke's law, where how much you stretch the spring is my delta S. And in this case, force by the spring would just be the weight of the block. Because it's not accelerating, it's not going anywhere.
And just to clarify, delta S is just the spring at equilibrium with Waitman, right? Not the extra. Like-
Yeah, if you pull it down further, the amplitude never has anything to do with the timing. And so in some of those homework problems, we told you how far it stretched to the new equilibrium. And then we pulled it down an extra amount just to see who would use it. Again, evil. Yes.
Can we go over, let's see, it's part D of problem 1 on another sample final exam?
Sure. So. We found in part B that the amplitude was 20 meters, right? And we know that when I have this horizontal system with any kind of a spring attached to a block, that there's an equilibrium position where the spring is neither stretched nor compressed. And then we have the turnaround points at x equals a and minus a. We usually call this x equals 0. Okay. Now, because the spring is neither stretched or compressed here, my net force here at equilibrium is 0. If I just attach the block to the spring and put it down there, it would stay forever. And so that's where my acceleration is 0. It's also where my speed is the biggest. Because it's speeding up as it gets there, slowing down as it goes away from that. The turnaround points, you've got to stop to turn around, so there's no velocity. But that's where the spring is either stretched the most or compressed the most. So that's where my A is my A max. And so if I want the maximum acceleration, I'm going to use Newton's second law. This is A max when delta S is equal to A, or at the turnaround point. And so if I draw a free body diagram for the block, I have weight down, I've got normal by the track up, and then I've got this force either to the right or the left, depending on which turnaround point I'm at. And that's going to be given by Hooke's law. But at the turnaround point, delta S is equal to the amplitude. And so in this case, since I have a K value of 1,000 newtons for each meter and a amplitude of 20 meters, this force, which is the net force, is going to be 20,000 newtons. So I can put that in here. The mass is 400 kilograms. Right, yeah. And so now I just solve for A max. Back here first.
Would you actually mind going through the first 2 parts of that question as well?
Oh, the first 2 parts. So the first part is really not from this part of the course. This is from the energy part of the course where I had gravitational potential energy here and I had kinetic energy here. And because this is a friction, oh, sorry. I have gravitational energy here, kinetic energy here. Because it's a frictionless track, those are equal to each other. So if I find out how much energy I started out with, that's just mgh. And I have 400 kilograms times 10 newtons for each kilogram times a height of 50 meters. And that's going to give me 20,000, 200,000 joules. And then if I use my formula where this is Ka squared and solve for A, I put in 200,000 joules is equal to 1/2 times 1,000 per meter times A squared. And that's gonna give me A squared is equal to 400. And I just take the square root. Yeah.
I was just wondering for part E, they eject at the turnaround point. What could be the problem if they ejected at the equilibrium point?
Oh, yes. There's a really good reason why they ejected at the turnaround point. If they ejected anywhere else, it would become a very messy, ugly problem that would be beyond the scope of this exam.
Right.
Let's just not go there.
No one has questions on this one. You can answer those first. I was wondering if we could go to number 5
On the other exam or this
on
exam?
this one.
Sure. Joyfully. Yes. You remember that I encouraged you to bring graphing paper, okay? And I have brought this kind of graphing paper tonight. You see that the squares are really small and faint. It's a little bit better on this side. I have some paper, pads of it, with bigger squares on white paper where you can really, essentially it looks like this. And I had it right at the door. I was gonna bring it tonight, just hand out paper, but I left it sitting by the door. But I'll bring it tomorrow morning to my office. If anyone needs wrapping paper for that problem, just stop by and pick one up. So this is how you do it. The first thing you do is bring 3 different colors of pen. Okay? 3 different colors. Now, in one of the colors, what we're going to do is we're going to, let's do the free end here. I'm first of all going to redraw my original pulse. So I go over 3, I go up in 2, down in 1, over 3, down 2, over 3, up and over. Okay. Now, if it's a free boundary, I pretend that there's another pulse or set of pulses coming from the other side of the wall. And the way I draw those is I do a mirror image. And so this would go 3 over and then up in 2 and then down 1 and then over 3 and then down, over and up. Okay. Now, that's step 1. Now, if I were doing it for the fixed boundary, step one would look like this. 3, up and 2, down and 1, over 3, down 2, over 3, up. Okay, in this case, I would take the mirror image, but I would also invert it. So here it would be over 3, and instead of going up 2, would go down 2, back, and then over. Instead of going down for the square, I'd go up. And these guys are going this way. At the same time, these guys are going that way. Okay? Now, that's step one. Step two is you look and see how far they've moved when you're asked to find the shape. In this problem, we were supposed to wait 7 seconds and they move 1 square a second. And so these pulses are gonna move to the right 7 squares. So I'm gonna count 1, 2, 3.
Dr. Francis.
Yeah.
Move it again.
Oh, sorry. So 1, 2, 3, 4, 5, 6, 7 is right here. And over here, I'd go 1, 2, 3, 4, 5, 6, 7. Now, what that means is that by the time we look 7 seconds later, this part of the pulse to the right of my line is already back behind the wall where the spiders live. The only part that's still out in the daylight is this square part. So I'm gonna draw that. And that's just, I've got 2 squares. And then it goes down. Like that. Okay. On the other hand, everything to the left of this line is going to get out into the daylight. And so it's going to go out 1, there's the 1, and then I go up 2 and down 2 and over. So you see I've used 2 different colors. Now I take my third color and I add them up. Well, here I have 0 and 0, so that's 0. And here my square, my pencil pulse, the square pulse is 0. So it's going to be all the red pulse. And then I hit this point here where the square pulse goes from 0 to -2 real quick. So now I have a +2 from the red pulse, a -2 from the pencil pulse, and that's going to be 0. I'll go down to 0. And then I just add them up. Here I've got a +1, and here I've got a -2. Well, that's -1. Here I've got 0 and -2, it's -2. And so it's gonna go down like this. And then the red pulse is 0, so all I've got left is the square pulse. And so what it's going to look like is that. Yes. Yes, sir.
How do you know, you said on those initial pulses, those little dividing lines, how do you know where to put those?
Did someone hear him?
So you put those dividing lines on the initial pulses, but how do you know where to put them?
How do I know where to put the dividing line?
It's 7 seconds. That's what the question says, at 7 seconds.
Oh, I counted 7 squares over because we're told in the problem that we're supposed to draw the pulse 7 seconds later We're told that it's moving 1 square per second. So I counted 7 squares over back here.
How do you know that it? The seconds. How did you know to like move it to 2 squares?
Oh, I didn't. I was just looking for some graph paper.
Oh, okay, but if we stay on the same level.
My graph So. That's
Well, that's something. We're pretty solid. That's important stuff. You know, he made it.
let's do the fixed boundary on a whole new piece of paper. I would. The
We're showing.
square pulse would look like this. And now the red pulse on the other side can be taught. Okay. So now the parts that are overlapping each other, this is the square pulse. That's where it cuts off there. So I've just got this part here. And then I've got this part that's coming to the daylight here. And now I add them up with another color. Again, I've got 0 and 0. Here, the square pulse is 0, so it's just the red pulse. But when I get to here, I've got -2 from the square pulse, -2 from the red pulse, and so that goes to -4. And then here I've got -1 and -2, that's -3. And here I've got 0 and -2, that's -2. And so it's gonna go like this. And then I'm just gonna have the square pulses all like that. Okay.
Questions?
Yes.
Could we talk about the mock cones and how to set up the triangle, please?
Yes, the mock cone problems, and there is one on the exam. Oh.
Yeah. Just a new.
They come in 2 flavors. But only 2. Okay, so that's good news. In one flavor. I tell you. I tell you how high the plane is above your house. And how far it goes before you hear the sonic boom. Okay. Now, the key to these problems is finding this mock cone angle, or really it's the mock cone half angle of the cone. And if I know these values here, I can use the tangent function to find that angle. It would be the opposite side over the adjacent side. So the angle would just be the inverse tangent of each over x. Now, once I know that angle, I know that speed. Okay, because the sine of that angle, remember, was 1 over the Mach number. And that means I can say the Mach number is 1 over the sine of that angle. So once I find that angle, I can find out how fast the plane is going.
Okay.
Now, that's the first flavor. The second flavor is the opposite. I tell you how fast it's going. I say, plane going Mach 3. And from that, you find the angle now. Once you know that angle, you know everything about the geometry. If I give you the H is equal to 1 kilometer and say, what's X? You can do that. If I say X is equal to 2 kilometers, what's H? You can do that. Okay, so those are the only two flavors.
Okay, perfect, thank you.
We are running out of time. Let me just reemphasize the fact that I will be in my office every day, not Saturday, but tomorrow and all next week after 9 in the morning. So,
When do you leave?
be around 3. So. Unless you've made an appointment. The help center, we've asked the TAs to, see if they can take time in there without moving their own classes. Have them to do so. Yeah, it's completely voluntary in their plan. No one's in that. Good luck, people, I'll be.
Thank you, Greg. We love you. I love you, Greg.
Yeah, you got it.
It's too crazy. Crazy.
Right now.
Never saw.
I think I'm like.
Great.
Right now, right now, right now, right now, right now.
Oh,